Hello again, everyone. Welcome to Comp526 tutorial 7, where we'll be going through the 3 exercises provided for us this week. So let's begin. Problem 1, move to front transformer. So let S be this input sequence of numbers, which values are initially stored in this list, which I have over here. Build an output sequence and trace the content of Q throughout the execution of the move to front algorithm. So this is quite simple to use, so let's assume, here I will be, in the yellow column, I will be storing, I will be showing each time we are examining one value from the input sequence. Here the yellow columns will be my array, my list Q, and here it will be the positions where the output sequence that I'm recording. So let's begin. At the beginning, let's say at round 0, we have list 20, 30, and 40. The first value in the input sequence is 20, which can be found at position or index 0 of my list. So I'm just going to record that position in the output sequence. So the first value is 0 because the first value of the input sequence can be found at position 0 of my list. Now normally, once I match a value from the input sequence with my list, what I do is I move that value at the beginning of the list. But obviously here, 20 is already at the beginning of the list, therefore there is nothing for me to do. So I'll just copy that list exactly as it is for the next value in the input sequence. So next round, second value is 30. 30 can find at position 1 of my list. Therefore, I write 1 here. And I have to move 30 to the front, so what I do is, first value of my new list has to be 30, and then I put the rest of the values in the order they were before. So after that, I put 20, then I put 40. Okay. Next round, next value I have is 30. 30 can be found at position 0 of my list, therefore I write 0 here. And after that, I move 30 at the front. It's already at the front, therefore I just have to copy my list like it was before and move on. Next value is value 20. Value 20 can be found at position 1 in the array, therefore I write 1 in my output sequence and then move 20 at the front, so 20 goes there. Then I write the rest of my values in order, 30 and 40. Next value, 40. 40 can be found at position 2 in my array, so I'll write 2 here, move 40 at the front, and then I copy the rest of the list in the same order. Okay, so we're here. We just did 40. Next value is 30. 30 can be found in position 2 again. So I write 2 in the output sequence and I'd move 30 at the front. And then I have 40 and 20 in the same order as before. And now I just noticed that I have copied the stuff over here as well, so I'll just be continuing over here. Next value that I find is 20. 20 can be found at position 2 in the list. So I write 2 here. So for the next round, my list will have 20 at the front and 30 and 40. Next value is again 20. 20 is at position 0. So I write 0 here. So for the next round, my list should have 20 at the front and have the rest of the values in the same order. Finally, 20 again. So 0 here again because it's a position 0. And my list is not changed because 20 was already at the front. So my output sequence would be 0, 1, 0, 1, 2, 2, 2, 0, 0. And this is the content of Q in each round. And we have everything that the exercise asks us for. So once again, to sum up, what we do is each time we look at the value for the current round, we find where the value is, we record that position in our output sequence, then we move that value at the front of the list and continue doing the same um, until we do the same thing for all of the values in the input sequence. Okay, so we'll move on to the next exercise afterwards. So hello again, everyone. We move on to exercise problem 2 for this week's tutorial, where we have to do the Lempel-Zeev-Welch compression. So given a word W, which looks like this, over the ASCII character set, which is provided over here, construct step by step the Lempel-Zeev-Welch factorization of W, which is the phrases that are encoded by one code word, and provide the compressive representation of W. This has to be done only using integer numbers. No need to use binary encoded, which would make it a bit more complex. So if you're not familiar with this, I suggest going to see Sebastian's lecture, where he has one video on how to do the compression. It will be very helpful. And I'll try and do the same here to try and explain it if that video was not clear enough. So what we do for this type of compression is, here we have our phrase. What we do is we try to find each time we try to find the longest substring that has already been encoded within our dictionary. Okay, so this is our dictionary. These are the positions in the dictionary, and this is what character is stored in this position. So let me give you an example. Okay, in the first round, I'm looking for the longest substring starting from the beginning of my string that has been encoded in my dictionary. Now, obviously, my dictionary only has single characters, so if I start from A, obviously, let's say SAS cannot exist within my dictionary already. So obviously A is a single character that has been encoded, that exists in the dictionary at position 65. So what I'm doing is I'm going to encode A, this single character, into a phrase. I'm going to store its position, okay, 65, and the final step is to add a new, let's say, code word within my dictionary, a new substring. And the new substring that I'm supposed to add is the phrase that I have encoded plus the next character on the original string. So since I encoded A, what I'm going to add here is A plus the next character, which is AS. So I add, AS at position 128 of my dictionary. Okay, we start from position 128 because the ASCII characters are stored in a dictionary starting from position 0 up until 127. So obviously the next one that we will be adding will be at position 128. So this is what we do iteratively, starting from the beginning of the string until we reach the end. So for the next one, A has already been encoded here. So we move on to S. But now we try to find, again, the longest substring starting from S that has already been encoded. So we try to see if SN has already been. Obviously, it's not been, because here we have only single characters, and here we have AS. So SN has not been already encoded, so the only thing we already have in the dictionary is just the single character S. So we encode S, single character S as a phrase. That can be found at position 83 of our dictionary, so we write that down here. Now we need to add the new code word, which is S plus the next character, that means here we have SN. Move on to the next one. Now N, we'll look for the longest substring here. Check for NX. NX has not been does not already exist in our dictionary, so we'll just write N here. This is what we're going to encode in this round, and can be found in position 78. And we add a new code word in our dictionary, which is NX. It's the word we have, the single character we encoded before, plus the next character, which is X. So NX. Then, same thing. XA does not exist in our dictionary, so we just have the single character X. So we take x, we add it here, and we add substring xa to the dictionary. Okay, so here's where things change up. Next position to start would be A. Check for AS. Now AS already exists in our dictionary, so let's see maybe that even a longer substring may exist. ASN obviously does not exist, so AS is the longest substring that exists right now in our dictionary, so we write AS here to be encoded. Now AS can be found at position 128, so we write it down here. Now we have to add a new word in our dictionary, which is the phrase or the substring we encoded, AS, plus the next character, which is N. So in total, we add the new substring ASN. Nope, ASN. Yeah. So since we just encoded AS, we move on to the next character that has not been in the substring. So we are at N. Let's check, is NA already in our dictionary? It's not here, it's not there, so we are just going to encode N. N can be found again at position 78, and we add substring NA to our dictionary. Let's move on. Afterwards, we start from A. Let's check AS already exists in our dictionary. So let's check that maybe ASN already exists as well. Yes, ASN exists there. Let's check for ASNA. ASNA does not exist, so the longest substring that exists in the dictionary right now, starting from A here, is ASN. So we encode that as a phrase, ASN. ASN can be found at position or index 132, so we write that down. And we add in our dictionary the code word ASNA. Finally, A is the last part of the substring that has not been encoded. So, obviously A has nothing left afterwards, so A is going to be encoded. A can be found at position 65. And since we're already done with the substring, there's no reason to add any other character, or sorry, any other substring in our dictionary. Therefore, we're done. Now, in order to find the compressed representation of W, we can just say that it's text C, and text C is equal to all of the positions that we have stored here in order. So it's 65, 83, 78, 88, 128, 78, 132, and 65. So this is the compressed representation of W using the Lempel-Ziv-Wells compression. Okay. I don't believe I've forgotten anything. Yeah. Obviously, since this is going to be stored, this is using the C as the representation as C. If it's gonna be stored as phrases, it would be stored like this. So A, find a good way of showing this. A, S, and give me a second. I'll write this down. Next. Yeah. This is how the compressed representation would be stored as phrases. Yeah, and we're done with this exercise as well.